about what I've been doing at Satellogic for the last couple of years. Well, at Satellogic we built and operate satellites for capturing images of the Earth, and we set ourselves quite ambitious objective, that is to be able to do image processing on board. So let me tell you a little bit about the problem. Okay, this is not a slide. This is a guide for the stuff for me to show you. I have a few cool images and videos taken with our satellites. Okay, these are a couple of color images. Well, not too bad given the projector. There you can see a few roads and fields and houses and stuff. This is another one. This tells something about how we build color images from different images of different parts of the light spectrum. And this is more about the same. And well, this is nice. This is built from 150 individual frames, each one 25 megapixels. So I don't know how many pixels does this image have, but it's a lot. And what you see that looks like a staircase are the edges of each frame. So a lot of frames cover the same area, and that allows us to make us for much better quality. Here maybe you can see a bit. Yeah, you see that over here the image is quite grainy because this area was taken from a single frame, and here another frame, and this frame and these frames are combined here, and it's less grainy. And as you go towards the center of the image, the graininess and the noise essentially vanishes, and this gives better signal-to-noise ratio and dynamic range for the image. But in order to do this, the images need to be rectified. So let me tell you a little bit about the problem of taking images of a round object. Okay, this is our planet. Okay, here you can see South America. Okay, it's a kind of sphere. But if we try to make a two-dimensional image, like a paper print or a computer display of a spherical object, we need to put it in some 2D space, okay, like this sheet of paper. So if we try to draw a 3D object in a 2D sheet, let's see what happens. It doesn't really work, okay? The problem is that the sphere is curved in two directions, and a sheet of paper you can only curve in one axis without destroying it, essentially. The other axis, one axis you can curve, the other one must remain straight, okay? So this is the essential idea of making maps, essentially. So what we need to do, Hernan is around. Maybe you, yeah, I'm not calling, but I need you to grab the microphone. Thank you. Okay, so what cartographers do is to try to match a sheet of paper to the world without ruining it. So the way we choose to do it is to do what is called a traverse Mercator projection, that is to place this is what we want, South America drawn on a sheet of paper. So we put it over the world like this, and we make all the points in this vertical line to actually touch the Earth. Okay, so it goes like this. And only the points in the straight line actually touch the sphere. All the rest are not touching it, are separated from it. Okay, so points around this line are translated very easily from the surface of the sphere to the paper, and without distortion. And as you go further away from this line, then there starts to be a distortion. And on regular maps, using the Mercator projection, you see that Greenland looks bigger than Africa, for example, something like that. And that makes absolutely no sense. This is because Greenland is too far away from the line that is touched to the sphere. Okay?
I'm intrigued about the plastic bag.
Well, the people from the Secretaría de Extensión, I don't know how to say it in English, from the university here, were nice enough to give me this ball, and I need to take it back. And as it is new, I thought I could use the plastic bag to draw South American apes. That's it. No. Okay. So, and we have this problem, but we have another additional problem, is that if you want to take a look at South America, it would be great. Thank you. It would be nice to look at the world like this, okay? With the area you are interested in closest to your eyes, okay? But that's not what will happen. If you are lucky, maybe you will look it like this, okay? A completely slanted view with a part that is much closer than you than the other, and the other one closer to the horizon. Okay, that's perspective, okay? And as a difference with the perspective views we are used to when taking images with cameras here on the Earth, here the roundness of the Earth is very relevant too. So let me show you something of this one. The kind of images we can get. Okay, this starts very nice. This is an actual video taken from our satellite. Okay, and this is Bolivia, and it goes pretty smooth. But a few seconds later, I don't have much time, so I don't know how much time to spend on this, but you see it looks nice. A bit later, okay. 2:20. Okay. Bueno, vamos. But this is a bit too late. Yeah, it's a bit earlier. Something around here. Here you see that the satellite was looking downward, and now it's tilting to the side. And to the side, the perspective changes, and things get smaller, and it can see further away. So here you see the border between South America and the Pacific Ocean, and at the end of the horizon, and above the horizon, deep space. Okay, so we want to take that kind of images and turn them into a map-like image, and that is not that easy. Okay, so what we want to do is to take something like this, for example. Yeah, why not? And turn it into this, okay? It's not trivial to do this. So essentially the problem we want to solve can be shown with this, okay? There you see the view we have of the terrain looked from a side with part of the hills occluding the view of the parts behind, and on top of that what we wanted to see, where each pixel of the image above is related to a point on the surface and is vertically above it. Okay? I will show you another video just because it's incredibly cool, although it has nothing to do with this. This is very new. I think it was downloaded today, yeah. And I only saw it a little while ago. Oh, it was loading it.
Oh, the other one this is very good.
This one or the other one?
No, that's good, very good, but it's not the best.
How come? Look at those cars over there on the highway. It's amazing. We are 500 kilometers above there and we can see that. I still can't believe it. Okay, here as I show the other one.
This is good.
And well, these videos are obviously sequences of images, and we want to do stuff with every one of those images to build a stripe like the one I showed you before. So
Those videos are raw.
Yeah.
Not rectified, not
completely unprocessed. They downloaded like that from the satellite. We did nothing to them, just to show them to you.
How long it takes to download the
not much. No. It's not. Today is not important. It will be soon.
Okay, so what we have is a planet with a rock surface on it with mountains and stuff, and far away from it we have what we call a pupil, what is the front end of a camera, and a little behind we have an image sensor, okay? And rays of light, we can think of light that way for this, that is a field called geometric optics. We can think of rays of light that come from each point of the surface of the Earth towards the sensor, and all of them meet at the pupil, okay? So the point in the sensor the light reaches has a relation with the point of terrain that part of the sensor is looking at. But that's not what we want. As I showed you before, what we want is the little drawing on top shows a part of an arc of the circumference of the sphere where I put the piece of paper and I draw little lines to the sides. And a cut of that is this, where we see that we have the piece of paper, and on each point of the paper we want to paint some color. We want to look straight to the center of the Earth and see what we would be able to look over there. So we want to build that from that. Okay? Okay. Yeah, there are two things that we need to do. One of them is for each point in the rectified frame to find the top of the mountain, the part of the Earth it's looking at in 3D space, and from there go to the sensor and the raw frame to sample a value. Okay? The first part is much harder than the second one. The second one is just to specify a mathematical rect that goes from the point on the Earth and goes through the pupil and see where it intersects the plane of the sensor. That's pretty easy to do. This first part is much harder because we don't have a good description of the surface of the Earth. So that's what makes it pretty hard. So what we do have is what's called a digital elevation model that for some point specified in latitude and longitude it specifies an altitude above sea level. That's the usual GPS coordinates, right? And the Earth is not really a sphere, it's modeled as an ellipsoid. So I exaggerated it a bit to make it more easy to see, but we have the stripe, the rectified stripe over there, we have the ellipsoid, and we know point A, and we want to know point E. But what we can query if for some angle of latitude B, it's easy to compute the point C on the ellipsoid, and from there we can query the digital elevation model height that I call B, and then C plus D equals E. But we want to look through the slashed line that goes through the center of the Earth, but the digital elevation model is expressed on this angle that doesn't go through the center of the Earth. So this requires why not?
No, where it goes?
It's not well defined. What is defined is that the line of the angle B is perpendicular to the tangent or to the ellipsoid at point C, and that's for historical reasons. Okay, so we need an iterative algorithm that finds C, and then the rest is just easy. Okay, I think I'm done with this. Okay, so now I will show you the code that does exactly that. Okay? Okay, I'm lucky, it fits in the screen. This code has a few arguments, okay? The frame and what the specification we have for the view of the satellite is a position of the satellite and the attitude, how it is looking at the Earth. So the position of the satellite is where it is, and the attitude is where it is looking in a kind of an angle. This is all done in X, Y, Z coordinates in a system we call SF that is centered at the center of the Earth. And the attitude of the satellite is a quaternion. So we have that information. Please disregard the bound stuff because I don't have time and it's not interesting. So what we do is to iterate over, we build the rectified form and we iterate over its pixels, okay? And for each pixel XY on the form we are trying to fill, we ask the stripe, the object that represents the sheet of paper, for a point on the sphere that corresponds to that point on the sheet of paper. The point on the sphere is 3D. That is rather cheap. I believe it costs 15 floating point operations. And then with that we ask for SF on terrain 4. That's the iterative method I just told you. And then we have the point on the top of the mountain, and this difference, Earth on Earth surface, SF on Earth surface, less telescope pupil in SF, is the direction that the telescope needs to look over there, expressed in Earth coordinates. But we need them expressed in satellite coordinates. So we do this conversion inertial to body, that is essentially apply the quaternion. And then we have a direction in satellite coordinates. And then body to sensor, translated that, project that on the focal plane. And those are the coordinates we need to sample the input and just fill the output. So it's not that complicated, if you wish. Maybe I can show you a bit about this code. Well, this is the point going from the sheet of paper to the sphere is interesting because the y coordinate is always is computed as a point on the tangent on the sphere, and the x goes away from the sphere. So they are computed in different way. The center point for y is done using a slurp that is a spherical linear interpolation and using a bit of trigonometry and stuff to go, because here in this direction pixels mean angle, okay? And in the other direction, in the x direction, pixels don't mean angle. Pixels mean going on a straight line, to the side. So we have this 1 pixel to the left variable that is a 3D vector that goes 1 pixel to the left. So, and we just multiply that by the number of pixels. It's easier, it doesn't require a trick. Okay? So this other one, that is the most complex one, we have several implementations. I will tell you about that in our way. But we have this reference implementation. This has to do with the digital elevation model. And as I did a fairly complete model of the problem domain, I implemented several digital elevation models. The one I told you about is the most basic one, and is latitude to longitude them. So it takes information for a data set that called Shuttle Radar Topography Mission that was done by the NASA a few years ago, and I asked it for a fraction. I did it a fraction because it's the constant k I need to multiply a radius to go from the sphere to the sheet of paper, and that's the expensive part, this one. And this is the iterative algorithm that iterates until done, and that asks for a candidate and does stuff and tries to converge. These are the costing floating point operations. Going from the sheet of paper to the sphere is 15. Going to terrain is unbounded because it's an iterative method. The difference is 3. The vector rotation by the quaternion using a matrix is 15, and then body to sensor is 9. This gives us about 41 plus who knows floating point operations. Yeah.
I'm sorry, but
please.
I don't understand why you have to iterate. When you cannot, I don't understand the algorithm requires iteration rather than solving an equation.
The reason why you cannot solve an equation is because at each step of the iteration we are sampling a data set. It's not a closed formula. The object that gives you the height at a latitude of longitude doesn't have a closed formula, so you cannot extract an expression for that. That's the central reason for that.
The equation says that you cannot solve it for your,
Yeah, of course. That's part of what of the fun. Okay, so we want to do a 25 megapixel frame in 60 milliseconds. That gives a total of about 500 million pixels per second. And the computer we have on the satellite to do this work is a low power CPU from AMD that they say, we give you 1.5 gigahertz and 4 cores. So in theory there is a maximum limit of about 6 gigaflops. But that is if the CPU is only doing float arithmetic and not running a real program or reading stuff from memory or writing results, okay? So that's why I call it PMPO, that is the false way to measure power in music system, and they say absurd numbers of watts that are not real at all. Well, okay, this is a bit like that. It's gigaflops PMPO, and it has a GPU that has 64 gigaflops. Okay, I need to hurry. 64 gigaflops doing 32-bit floating point arithmetic. But it's 16 times slower if you do 64. And we do need 64 because 32 is not enough because we are too far away from Earth, so we need many bits of precision. So we need to do that. We need about 20 plus something gigaflops per second in 64-bit. That's more than the GPU has. And if you set apart time for data transfer from GPU to CPU, it's even worse. So this is the approach I took to attack this problem. I started by studying the problem, understanding the problem, and doing a complete implementation in Smalltalk without any regard of performance at all. And so I learned that I could do it because I never done this kind of stuff. And I could validate results against reality. And most important, I built a baseline for comparison of later work. And I understand the structure of the code, of course. And then I started to iterate, okay? The approach I took, I didn't want to fight OpenCL too much. So what I did is to simulate the behavior of an OpenCL implementation in Smalltalk, including the simulation of the 32-bit arithmetic, wrap around the integers, the way the GPU does image interpolation, everything. And then I turned that into an OpenCL implementation and measure performance. And then iterated over this many times, and the kind of things I try to optimize, because it were experiments, I wasn't really sure, are no new ways to represent the elevation model that I didn't tell you, but uses over 60 gigabytes of space. So it cannot live in memory, so we also need to be careful with how we read parts of that information and stuff. Cache everything we can cache, and rewrite the algorithm. I found a way to rewrite the the calculations to do 64 precision complete calculations just for 1 point and do the 25 millions as local computation from there. So the distance I need to cover goes down from 500 kilometers to less than 10 kilometers, and then 32 bits is enough for that. Okay? So I could run it in 32 bit. And, well, iterate again against the OpenCL implementation and see how it goes. The OpenCL implementation could actually be derived from Smalltalk. We thought with her, who's here, about doing it in Halide, that is a framework for auto-generating GPU code, and we also, after Bert's experience on generating JavaScript from Slang, we thought about doing something alike to generate OpenCL from Slang. And at the end, given that we were rather short of time and of people, because I did it all by myself, essentially almost 95% of the work I did myself, we chose to hand translate. And as it was less than 100 or 200 lines of OpenCL code, that is exactly the same as in Smalltalk, it's not a big deal. So it was okay for this project not to invest too much on tools, but go ahead and do it. Okay, these are the results of the experience. I don't have time to go in too much detail, but the development was as we used to in Smalltalk. It was comfortable, it was safe, it was easy to reproduce and to understand what's really happening, and it was almost all the time in Smalltalk. And I can claim we have world record performance because we could extract from the GPU over 100% of the theoretical peak performance. This is including memory transfers and program control program. And the people who sold us the computer published one paper where their performance experiment was to run some standard algorithm in Python and OpenCV and recompile OpenCV for GPU and OpenCL. And we get 20 times more gigaflops than them. So they didn't really know what they were doing. Okay, so we succeeded in being able to run on the satellite stuff that is usually run on large computers on Earth and completely offline. Because for this problem, nobody has ever done a really optimized implementation. And this has to do with the Satellogic strategic plan of having hundreds of satellites in orbit. Okay, it makes no sense not to try it, because the overhead of doing it on Earth would be overwhelming. So this is what I learned from this experience. These are, I can say, the myth of high performance code. If you want high performance, you need to do C. Or someone else might say, if you want to do high performance, you need to do assembler. Or if you need to do high performance, don't wait your time. Use the best existing library. Well, I say no. If you want to do high performance, you need, and this is stuff I learned, I didn't know before. You need to know your architecture. You optimize for a specific architecture. You cannot optimize for an abstract general computer, okay? And that means platform-specific languages and tools. Maybe it's C, maybe it's assembler, maybe it's OpenCL, maybe it's something else, who knows? you need to pay attention to your architecture. And you need to optimize code. Optimized code requires, in my approach at least, malleable code, because I will iterate many times over it. And code that is always evolving. And coders that are always learning. And Smalltalk is very good at this. Okay, maybe you can say Smalltalk is slow, but that's not what matters. What matters is this. So, besides high performance, means knowing your problem well, and means willing to work hard. There are no easy solutions. Thank you.
My question is, okay, you last year, I think in the previous conference, you said something about this challenge that you already solved. So, what's the next challenge? Because this is solved.
Yes, last year I was about halfway the iterations, and I was still not using the digital elevation model. I was assuming the Earth was spherical to start with a simplified version of the problem, and the rest of the problems were the hardest one I solved afterwards. So in this year, what comes next? Well, I can tell you what I am working on right now, because in a month or two I don't know. Right now, you remember that what I said. The arguments to the rectification are the position and the attitude of the satellite. Well, knowing that is very hard. Okay, so right now I'm working on that problem. We are doing an alternative run of this very same code that is on Earth. Okay, and doesn't need to rely on the satellite capabilities for determining very precisely its own position and attitude. We will use both. Okay, so on Earth, what we can do and what I'm working on is using the images themselves and using a ground reference to find control points, that is pixels in the raw frame that we know the latitude and longitude, and use that to extract satellite position and attitude. It's a completely different problem. It's also very interesting, and it's what I am working on right on.
This is hard for the satellite to know.
The satellite is 500 kilometers on what 1 degree means in terms of pixels. So the precision is like crazy.
It's crazy. The precision we want is crazy, and absolutely nobody has it. Okay, so.
But the difficulty is in the precision of the quality of the image, not in the time required for the processing.
No, the problem why we are allowing this alternative approach is the limitation of the satellite to know its position and attitude independent of it being taking images or not. For position it uses a GPS, and for attitude it uses a star tracker, that is a different camera that looks at the stars, finds the stars and say, okay, if this star is over there, then I must be looking in this direction, and doesn't use the telescope, the main camera. And those are the systems against whose limitations we want to be ready to defend from.
Okay, so I just want to say that your last slide is absolutely right. It's a very important lesson. And I want to tell a story about the fastest system in the world. It's smalltalk, but that I was associated with. So this is actually about, we had a initial 88. That's how long ago it was. Carla Scaletti had a PhD in music, and she was getting a master's in computer science, and she could prove she was a computer music person. She was going off to get the job, but she wanted a master's. And she was interested in generating music from sound waves, where she crafted carefully every single sound wave. You can basically add sine waves together in something complicated. She had lots of different algorithms that she would use. And people could do it by plugging together different devices, and there's different ways people do it. She was doing it digitally. And she was running it, getting time on a cray, and like a 30 minutes on a cray to give you 5 seconds of the sound, and that sort of thing that she was doing. So again, she took smalltalk class. Actually, it probably was a little bit better than that. She did it on a Mac in Smalltalk in 87 or something like that. So it was really, really slow. It took a long time. She could crack it. So her husband had a project with electrical engineering PhD student. He was doing digital signal processing. And what she wanted to do was to write code with digital signal processing. So she would take she'd make a composition, it would be all these sound objects that you could put together, and then you would hit the play button, and it would generate the code, stuff it in digital signal processing. Now actually, the type of code, they had like a virtual machine for sound, a bunch of all these algorithms, and so what you actually were writing in were addresses of routines you would call. So it was sort of, they had a virtual machine inside the digital signal processor. Anyway, I had actually one contribution to this because she has a big tree of objects. Each object asks the other objects for their set of sound events. And what I said was, well, why do you take the whole set? Why don't you just have it be a string and take the next one, Because that way, then the whole tree, you'll be taking the next one, the next one, the next one out. And so you don't have to wait till you generate all of them to play. And so when she did that, you would build the whole thing. You would hit play. It'd be like 3 seconds, and then the music would start coming out. And it was literally writing code and sticking it in the digital signal processor as it was executing the program. If you didn't wait on it, it would overrun the program and start to get crazy things. But if you give it enough time, it would be generating the code ahead of the digital signal processor running the code. They have a company. It's called Symbolic Sound. The product is called Kima. Kima 7 is out. It's in Smalltalk still. It's basically these two people, they wanted to make a living off of computer music, and they've been able to do it. Not get rich, obviously. In Star Wars, the weird voices were actually run through Kima. So they have a list of all the different movies that have been made, but they use Kima as, and there's a lot of musicians that use it. So anyway, it's a Smalltalk. So world's fastest, the only generated sound, bit by bit. The craft your waveforms for sound. That system has Smalltalk is a core part.
Cool, thank you.
Thank you for sharing.
Is there any other question? Cool.